So I've just been introduced as a mathematician. I'm very, very rarely accused of being an actual mathematician. I'm closer to an applied mathematician, which a real mathematician will tell you is not an actual mathematician. But as a consequence, my research and my work is funded by various federal agencies and companies, commercial concerns. And just as a matter of full disclosure, we've received equipment and funding, various types of equipment and funding from Intel, AMD, Nvidia. I'm not going to let that color my presentation to you, and I'm going to be equally brutal about all of those companies. I had a bit of a rough week this week. My laptop, which is now called Blinky, does precisely one thing now. You turn it on, and it flashes a folder which says question mark, which I'm reliably informed means that the hard drive has died, which is curious because it doesn't have a hard drive. It's a solid-state device with SSD, so it's basically completely hosed. I put this up for a reason. One, I miss Blinky. It wasn't as bad as the previous Apple laptops, which used to give me a shock. I had one that actually would give me a light shock when I traveled. So when I'd plug it in the UK at 240 volts, that would sort of overwhelm the power supply, and I get this little zzz every time I touch the thing. But Blinky survived, actually, that didn't survive very long, about a year and a half before it decided to just go belly up. I like Blinky because it had several things going for it. It had an Nvidia GPU. So it had an accelerator, and I could, in fact, I had two. I could program that thing using CUDA. I could also program the GPU using OpenCL. I could program the central processing unit using OpenCL. So it was great. I could develop on the airplanes and test and do all my development work. I could use OpenMP on it. I could use MPI on it. It was great. It was also had other nicknames, Toasty, because when you ran the GPU at full tilt, the bottom would hit approximately 100 degrees. I mean, it was really it was lucky. I'm pretty lucky actually. I could actually have children because have this thing on your lap and it's gonna burn you. Why did I put this up here? Because it illustrates a point. That was a 2014 laptop from Apple. It came with an Nvidia GPU. I could use CUDA to program it. The laptop I bought from Best Buy on Monday, rather short notice, has an AMD GPU. I cannot use Nvidia's CUDA programming language to program that laptop now. That should be sort of an interesting caution to you guys. That if I'm going to talk, first of all, we're going to talk about CUDA, then I'm going to talk about OpenCL, then I'm going to talk about something else, the other thing that we're working with. And what you should be very cautious about is investing coding effort into a language which is locked to a single vendor. Suddenly, you can find your machine no longer supports that specific manufacturer's programming model. Okay? I think you've probably already, I looked at some of the slides, you've already heard this message in various different forms, that you don't want to get vendor locked into a single vendor solution for programming, because it takes you a lot of effort to program, and if suddenly that platform goes away, you're in trouble. I've got lots of other examples, but this is fresh. This is 2 days ago. My programming world on my laptop changed. It didn't impact the way I do business at all because I've insured against that. I've hedged against the failure of a single manufacturer or the disappearance of a certain platform. And I'll explain that as we go along. Blinky. Right. Okay. So I'm going to be frank. It's going to take you more than 3 hours to learn how to program GPUs. But I am going to take you down to the core basics of actual GPU programming using CUDA, OpenCL, and something else. Okay? So you'll see the structure of it. You won't necessarily grok the whole business, but you'll get a sense of it's actually pretty easy to program these things, but it's been made difficult, conceptually difficult, by some choices in the way that the programming models have been developed for programming these devices. Okay? So this is something just to keep in mind, that to be fully expert takes quite a while. I've been at this 7 or 8 years, and I still don't think I'm fully expert in GPU programming. There are still corners of these devices I don't quite understand. But in order to get up to speed, you can start to see what you need to internalize in order to be productive on GPUs. We're going to discuss basics, and there's a whole bunch of stuff. There's an active, vibrant GPU programming community out there. So there's a lot of stuff on the internet. We may or may not have some hands-on. It kind of depends. Haven't had a chance to investigate Argonne's clusters for GPU programming, but let me just do a quick survey. How many of you know if you've got a discrete GPU in your laptop? 1, 2, 3, 4, 5, 6. But I see some other apples, and it depends if you cheaped out or not. If you've got the 15-inch latest MacBook Pro Retina, you may have a discrete GPU and not know it. So the difference is about $2,000 versus $3,000 as to how much you paid for this thing. If you look at if you click the Apple button and look at about this machine, you can actually find out if you've got a discrete GPU. It'll say something like Nvidia GTX something or AMD something as the discrete GPU. And you might find you've actually got a GPU in there that you can use. Even if you don't, if you've got one of the later, I'm looking around, if you've got one of the later MacBooks or MacBook Pros, you might find it's actually got not a discrete GPU, but an integrated GPU. It's part of the Intel Central Processing Unit, may have actually a built-in GPU that you can use as well. It's likely it's not an AMD, it's not an Nvidia GPU, it's probably an Intel integrated GPU. And you can actually use that for the second part of this class, okay, for when we get to OpenCL. So some of you who've got Nvidia GPUs, you can code along as we go along. The others can just sit back and just marvel at the fact that you didn't spend the extra $1,000. And some of you have got Windows laptops. You're more likely to have discrete GPUs. And you can install NVIDIA's SDK for CUDA if you're feeling brave. OK, so let's keep going. You can get the slides from the workshop webpage, or you can get them from that directory. And I've also set up I have two Git repositories. One has a Git repository for examples just for this workshop. And then the second Git repository is a repository for the thing I'm going to talk about in the third part of the tutorial today. Okay? So we'll come back to that later on. Okay, so as I said, I'm a mathematician, so what the hell am I doing telling you about some nasty, esoteric computational science thing? Well, I'm sort of a mathematician. I'm sort of an engineer, sort of an applied mathematician, sort of a domain scientist. And I've worked with a team, and we have diverse interests, including creating high-performance versions of our PDE solvers. So when we create discretizations, finite element methods, finite difference methods, whatever they are, we want to move them into production. And we've done that. We've moved novel methods into industrial applications. They're actually codes you can buy out from companies which use the methods we've developed. And we want to make sure that the methods we're developing are relevant and useful and efficient on modern hardware. So we go all the way from developing methods to deploying them, and deploying them in production codes. So that's quite a industry. So I've got a group of people I've worked with from industry, also visitors, colleagues, postdocs, students, undergraduates, and so on. Now, I have the problem as the manager of this group that we have this fragmentation in accelerator programming. We're writing codes that can last for 20, 30 years. There are codes I wrote for my PhD thesis which still are being used and being actively developed. That was quite a long time ago. So we have to sort of, in some sense, future-proof these codes. One of the things we've developed is a way to try and future-proof the codes so that we don't have to refactor, recode, redevelop every time somebody creates a new multi-threading paradigm or platform, okay? So that's one of the reasons I'm talking to you today. As an educator, I have to decide what am I going to train my students to do? Am I going to train them to use CUDA, OpenCL, OpenMP, OpenACC, pthreads, MPI? How am I going to invest their time wisely and effectively? So sadly, I teach them all of that stuff, and then we integrate all those into a single abstracted framework, which we'll talk about, okay? But the interesting thing is, once they've got those skills, suddenly they're in rather high demand from companies. Bottom left, just graduated 3 PhDs this year, Rajesh, David, and Reed, and they've all had multiple job offers from companies including Goldman Sachs and others because these skills of being able to use CUDA, OpenCL, all these programming skills, and having their applied math training suddenly means that they are in high demand in industry. Okay? Oh, and the other guys, the other students at the bottom, they've all had internships. They've all gone to great places and all in high demand. Right. But I have to manage them. So I don't want them all to be programming in 10 different languages and I get 10 different unsupportable solvers. So we've unified the way that we program so that we have one approach to programming which encompasses all of the different programming models we're talking about. So we really do go from developing fundamental methods all the way through numerical analysis, acceleration, and scalability. And yeah, so various different physical applications. So I'm really an application guy, as well as a math guy, a computing guy. Yeah.
Was that slide on the top left, is that a spectral element tetrahedron?
Yes, of sorts. So if you look at the second one on top, that's a Nodal Discontinuous Galerkin book. So I'm a co-author of that book.
And that's got spectral DG in it, spectral element DG.
This is a complicated and very political discussion, but it's not quite the same thing as a hexahedral spectral element. The hexahedral spectral element has very special properties. This has some of those properties, but not the nice ones. But it's useful in the context, in a similar context. So we're positioning that element as a high-order Lagrange finite element, which can play nicely with hexahedral elements. In fact, we have hybrid grid mesh spectral element type solvers that not only have tets, they have prisms, they have wedges, pyramids, everything in there, so that we can glom onto the spectral element DG codes and be compatible with those. So I've seen like half the audience just glazed over at that point.
Sorry, just one quick question.
Yeah.
So does it have the orthogonality properties of like a
No.
hexahedral?
No.
Okay.
We have orthogonal bases for those, but as I said, it doesn't quite have the nice structural properties of the spectral element hexahedral element. But there are other things at play. So try meshing the world with the hexes and you'll have problems. Yeah. So we have all sorts of interesting things. So I can give a talk on each of these different things. And they'd be progressively less and less interesting as we go top left. But we've deployed these discretizations in all sorts of different applications. Okay. I'm kind of in two minds about this section. It's kind of a lightweight introduction to the difference between a CPU and a GPU. I don't think I want to really drill into that too much because it's kind of, it's a little abstract. So this is an old model single core CPU from AMD. I think it's in Isolese. And I just want to illustrate the disappointing thing about early CPUs for high-performance computing. So if you look at the architecture of, this is a die shot. These things can be beautiful. This is a very gray and boring one. But if you look at the real estate on the chip, what you find is that most of this CPU core is dedicated not to actually doing floating point operations, which is the thing I need to actually crunch numbers for those simulations. Everything in those simulations boils down to multiplication, multiplies and adds. Everything, when you look at really what gets done in updating the solution at any point in space, it just involves multiplies, adds. That's the fundamental building block of all HPC applications, typically, at least in my area. And you buy a chip, and you find out that down here at the bottom, that's the only part of the chip that's dedicated to doing those floating point operations. Everything else is management. I think some of you are at labs, and you'll appreciate this, that you're the worker at the lab, and then you're surrounded by managers. Or if you're at the university, this is like having all the university administration, including the faculty and the deans and the provost and the president, all those people who are relying on the graduate students to do all the actual work, right? The staff and graduate students. So there are technical reasons why this is the case. And in the GPU world, it's kind of a different world. So why was there all that infrastructure to support the one worker? Because the idea in the CPU is you want to keep that one worker busy at all times. So you have dedicated memory cache that makes sure that data is available when the CPU needs it. There is branch prediction to make sure that the CPU isn't going to stall in a stream of instructions. All that infrastructure on that chip was basically to make sure that that compute unit was busy at all times. In the GPU world, it's a very different story, where a typical task for the GPU is that you need to update the pixel intensities at every pixel on the screen so that a 15-year-old can shoot aliens. That's the task, right? And you want to do that at least 60 times a second. And if you think about a modern 4K screen, that's a lot of pixels. Millions of pixels, 60 times a second. But the thing about this picture is it doesn't matter in which order you update those pixels. Really, it doesn't matter as long as all the pixels are updated in 1/60th of a second. That's the core task. So if you have a worker on a compute unit on a GPU that's updating that pixel, and it stalls because it doesn't have memory, it doesn't have data from memory, the instruction streams are branched, it doesn't really matter that much in the grand scheme of things, as long as collectively they all finish in 1/60th of a second. So you don't have this notion of a primary thread that must be continually, must not stall. It's okay if a processing element on one of these, working on one of these pixels, it doesn't matter if it stalls or not. That's sort of not important. So the philosophy or the requirements of the GPU are rather different to the requirements of a CPU. Okay? So there are some historical reasons why the architectures are rather different. Essentially, throughput matters, single threads don't, and there are some other technical reasons. But if we compare and contrast that early AMD CPU with an early AMD GPU, you can see it's a rather different story. This is my dream. This is a whole bunch of graduate students, right? It's just a whole bunch of lightweight cores where they're not, cores is a bit of an exaggeration. There's a whole bunch of vector units, SIMD units, very little management, so very few faculty running this show, just one or two faculty, maybe a few more, maybe 15 faculty, running a whole bunch of graduate students. And each graduate student is typically going to be rendering a small number of pixels in that final image. Okay? So it's a rather different architecture. So how did they squeeze all those processing elements onto a piece of silicon? Essentially, it's a matter of getting rid of management. Your modern CPU core has instruction units, arithmetic logic units. It has out-of-order control logic, branch predictor logic, memory prefetch, so cache units. And in the early GPUs and large data cache, in the early GPUs, they got rid of all that useful stuff that means your program, your thread won't stall. They let threads stall. Got rid of most of the cache. Eventually, they put that cache back in, and I'll sort of get there in a little bit. So, if you think about that die shot, all those useful parts of the core diagram, all those useful all those things I've just wiped out, they take space. So once you get rid of them, you've got a smaller core. Once you've got a smaller core, you can fit more of them into the same piece of silicon. It's really that simple. So you've freed up, you got rid of the management, you've shot the management, you've got just basically workers left and their instruction stream. So you can fit more of those on. So in this case, let's just say we've got 16 of these. Now, we're just assuming at this point each worker has an individual instruction stream, a sequence of things they have to do, and they're all independent. But if you think about that process of rendering that image, the thread that's going to compute the updated intensities at 1 pixel is pretty much doing exactly the same sequence of operations, it's basically a bunch of computational geometry, as the thread is going to work on the next pixel, and the thread is going to work on the next pixel. They've all got the same set of basic instructions they have to process. So we'll get rid of some extra management, and we'll have just one instruction stream that will be used by all of the processing elements in this case. Instead of having one arithmetic logic unit, one processing element, we'll have 8 of them in this sort of abstract model. I've kind of just snowed you guys. That's kind of BS. This is just a core with a SIMD unit, right? Single instruction, one instruction fetch decode unit, multiple arithmetic logic units. It's a vector unit. That's sort of the hidden truth about GPUs. Each core on a GPU is basically just a wide SIMD unit. So what is the fundamental difference between a CPU core and a GPU core? In the CPU core, the SIMD units are not entirely central, right? There is the math, the floating point unit, right? So you have the main stream of instructions which feeds vector instructions through the SIMD unit. In the GPU core, it's all vector instructions. Does that make sense? There really is no, well, that's sort of the fundamental difference between the CPU core and the GPU core. There are some extra nice features of a GPU core. Because they want to be stall tolerant, they want it's okay if the instruction stream, if it stalls on the SIMD unit, that's fine, because you've got a lot of workers. But the trick they have is they have fast context switching. So if one instruction stream, or the processing elements working on one instruction stream, fail or stall because they don't have data, because it's high memory latency from the processing elements to the main memory and back. If they stall, fine. Switch them onto a different stream of tasks. Okay? So that's one of the very nice features about a GPU core, which is that they have fast context switching. And then because these cores are fairly modest in total size, duplicate them. So it's just like a typical multi-core CPU, except the structure of each core is slightly different in the sense of it's SIMD to the core. SIMD to the core, because every operation is performed at the SIMD level in the GPU core. And then there are multiple GPU cores per processor. Does that make sense? That's the essential structure of the GPU core and the GPU chip. There are some issues because if you think about every instruction is fed through the SIMD groups, what do you do if your code branches? Your code branches when you have an if statement. If this, do something else, do something else. Some of the SIMD lanes will go through one part of the branch. Other SIMD lanes will go through another part of the branch. So what do you do? Well, it's not, on the GPU core, it's not quite SIMD. It's what they've branded SIMT, single instruction, multiple thread. A thread working in the SIMD group, or SIMT group, can either execute the instruction, the same instruction as every unit in the SIMT group is doing, or it can execute a non-instruction, a NOP, a non-operation, okay? So branching is handled by basically lack of parallelism, or loss of parallelism. So if you have 32 threads running in a SIMT group, one of them might do something if it goes through the active branch in the if. The other 31 may do nothing. Will do nothing. So you either do what is in the instruction stream or you do nothing, depending on whether you're supposed to go through the branch or not. So suddenly there is a little bit of a difference between the GPUs and the CPUs. CPUs have branch prediction and doing all sorts of fancy operation management to try and make sure that threads aren't stalling. In the SIMT GPU world, branching can be catastrophic, and especially deeply nested nasty nested ifs, right? If you have 10-level nested ifs, every thread will go through every statement in that sequence of ifs. So there are some tasks which are suitable for GPUs, cores, and some tasks which would be catastrophically bad, right? As you would idle most of the threads if you have a deep logical tree and you only execute some leaves in that tree. Okay. And as I said before, there is fast context switching so that there's no magic, there's no magical unicorns or anything on a GPU. It is also bound by the laws of latency and physics that if you're going to fetch data from main memory, which is at some distance from the device, there's a long latency, long travel time for that request to be met. So as I mentioned before, if you've got a bunch of threads running through these ALUs, if they stall, then there'll be a context switch. And going back to this ethos of the GPU design, as long as all the threads get their job done in 1/60th of a second, great. It doesn't matter they stall. Yes?
A GPU ALU is predominantly for single precision data?
It's a matter of counting. Most GPUs for consumer graphics, for 15-year-old graphics cards, graphics cards 15-year-olds, they have predominantly single precision floating point units. Some of the more expensive professional level or compute level cards have actually more double precision floating point units, but still only a fraction of the number of single precision units they have. It is possible to get double precision arithmetic out of a single precision floating point unit by multiple passes, but you do lose some performance because you're basically doing double precision in software.
So even the GPUs that are sitting on a cluster, they're still predominantly single precision?
It depends. So in the oil and gas industry, they're quite happy to work in single precision. You can do seismic imaging quite well in single precision. So if you look at the cards that Nvidia's been selling to that industry, so the K10, the K20, and so on, they have a large number of single precision units. There are some more expensive cards that have more double precision units. But you can get good, if you're willing to pay, and when I say pay, I'm talking thousands of dollars, you can get the high-end cards that have quite a large number, so not as catastrophically poor double precision performance. All of those simulation results I showed you, all that stuff, oh, works fine in single precision. But there are some applications where you do need it. Does that answer your question? Yeah. So it's sort of a depends answer. Yes?
Something very related. Down to the core, it is different, is it? The single precision cores and the double precision.
Oh, I've got a diagram, and it will show you, sort of, in some sense, the structure of the cores. But I just gave you sort of an abstract sense of what the difference between a CPU and a GPU is. And I'll drill down into a GPU core and show you the structure. Any other questions? These are good questions. OK. So let's just summarize what this abstract notion of a GPU is. Multiple cores. And I'll get to, there is a certain issue with the word core. And I'll come back to that in a little bit as to what actually a core is. Each core has one or more wide SIMD vector units. They're typically 32 wide SIMD units. So you'll expect to feed your instructions through in batches of 32. You really need to find 32-way parallelism in your application. Each wide SIMT vector unit executes one instruction stream. Each core has a pool of shared memory, so they have a scratch pad, which the threads running on a single core can communicate through a scratch pad. So it's an interesting hybrid model. It's a shared memory model. It's a two-level shared memory model, and we'll get to that. And each core can hardware switch between multiple contexts to hide memory latency. But branching code involves serialization. So if you sort of internalize these notions, you don't really need to worry too much about the specific structure of the device. Just think about it in these terms. These sort of pick out some of the differences between GPU and CPU cores. I'm just going to specialize to one manufacturer and manufacturer's solution for programming these GPUs. And this is a sort of, I'm giving you a historical trend. OK. So I'm going to talk about Nvidia GPUs. And I'm not endorsing them. I'm just presenting this as devices that came to the market and talk about these devices. So here's an example GPU card. The structure of GPU cards is changing over time. In a couple of years, this will be really outdated, and I'll have to update my slides. But for now, it's not too far off what a typical discrete GPU that goes into a workstation looks like. This is an older one. It's a GTX 590. So this is a card. See that red arrow? This is technically a daughter board that plugs into your motherboard. Not in your laptops, of course. This thing's as big as your laptop. Not quite. It's about that big. That thing plugs into your PC. For the younger ones amongst you, a PC is a box about yay big. Sorry, I couldn't resist that. It's a wide bus. And every instruction and all data that you need to communicate through this daughter board goes through that bus. This is a quasi-autonomous compute device. It's basically a computer. It has all the features of a computer a typical computer, except it depends on the host. It depends on the PC you're plugging it into. Because it gets all its instructions from the host, which is instructions and data fed through that bus. In this specific model, there are two GPU chips. You can maybe see them here. Yes, this is a little bit old. This is 2 generations old machine, or card. Each of these GPU chips has its own memory supply. So it has its own onboard memory. Even though those chips are the memory chips are pretty close to those GPUs, there's still travel time. There's still time it takes to transmit bits from the GPU processor to the memory and get data back. And that's one of the causes for that high latency. Okay? There are independent, each of the memory comes in independent chips, so there are multiple memory managers. So there's some parallelism in the way that you talk to these chips. They can be, you have to be actually quite careful to make sure that you don't put all your data in one of those memory chips. Otherwise, you'll invoke the wrath of something called partition camping, where you have 6 memory managers, but you're only talking to one of them. Okay? But I've never satisfactorily figured out how to program against that, because I don't know exactly how the physical map between the linear array space on the GPU and the chips is set up. So we won't get into that. But that gives you a sense that this is an independent compute device, in this case 2 compute devices sharing one board. The interesting feature for HPC is, although it's high latency memory, it's high bandwidth memory, relatively speaking. So in this card, I think it was some 150, let's say 150 gigabytes per second or thereabouts. In the latest cards, you can move data between those memory chips and the processor at around about 330 gigabytes per second, which is quite a bit faster or quite a bit higher bandwidth than you get on a typical CPU. So my knowledge is probably a little out of date with Intel's latest specs, but let's say you get 50 gigabytes per second on an Intel chip, you can get 330 gigabytes per second on an AMD or an Nvidia card. Okay? So for moving data around, this is a pretty good chip, pretty good solution. So if you've got a data that needs to move, a lot of data that needs to move. However, having said that, the amount of storage on this card is limited, because those memory chips are the total memory for this device. In this case, it was like 1.5 gigabytes per processor. So it's about 3 gigabytes for the whole card. So if you're going to compute on this board, you'd have to cram your calculation into 3 gigabytes to get the high bandwidth. If your problem takes more than 3 gigabytes, you need more than 3 gigabytes of resident data, you would have to shuttle data across that PCI Express slot. And that PCI Express slot has a much lower bandwidth than the bandwidth between the RAM onboard and the onboard chip. Okay? So there's a memory hierarchy here, which is actually quite a harsh memory hierarchy. And we'll get back to it. So it is a quasi-autonomous compute device, and it requires power. So it actually has its own power lines. So it doesn't draw all its power through the PCI Express card slot. It gets power through some external power supply. And that's one of the limiting factors. The PCI Express standard says that this card should not draw more than 250 or 300 watts. Otherwise, we could have even more powerful cards, but that's one of the limiting factors. The total power budget is dictated by the PCI Express standard. Okay, so here's an example where we have a motherboard. We have some Intel chips being cooled by some monstrous cooling devices, some memory on the host, and then you have these extra cards that slot in. Okay, so the chip on that card was a Fermi chip. It's one of my favorite Nvidia architectures. It was actually quite straightforward and delivered good performance. We've got a diagram of the chip. So chip is, oh, I wish this would move. So you can see the chip there is on the card, and then if you look at a schematic diagram of that card, you'll notice that it's very regular. There are 16 of these, what Nvidia optimistically calls streaming multiprocessors. That's what we called a core. Okay? So that block there is one core, and there are 16 of those cores on this chip. If you look at the structure of that core, it's got, oh, I was kind of lazy here. So I stole this diagram from NVIDIA's documentation, and it says each of the processing elements on that core is a core. Well, there's some politics here. So NVIDIA wants to say that they have 2,880 cores per chip. Really, they have 2,880 vector lanes, processing elements. These are not really cores because they don't have their own independent instruction stream. So if we define a core as a piece of silicon with its own independent instruction stream, then they have 16 cores, and then in this case, each core has 32-way parallelism. Okay? A 32-wide vector device. So if we look at this architecture, you'll see that it has its own instruction cache. It has 2 schedulers, has a register file, has 32, let's call them arithmetic logic units. And then, I wish you could see this, but they have load store units and they have special function units. Then, with the 32 processing elements, you have 64K of shared memory. I'm right up there, I can't read it, so I'm having to sort of interpret this for you. This is a fantastic device. It was pretty much ahead of the competition at the time. It could deliver, theoretically, 1.4 teraflops. I never was able to get up over a teraflop out of this device. I was probably more at 700 gigaflops per second in single precision. And we can see why. So you could stream data between the GPU chip and the GPU memory at about 50 gigafloats per second. So 50 billion float could be moved backwards and forwards between this processing unit and memory. But it could do 1,400 gigaflops per second. So in order to get to 1,400 gigaflops per second, divide 1,400 by 50. What is that? 28? So you'd have to do 28 floating point operations for every float you load or store. Now, if you think about your application, think about the thing that you're working on as your day job, whatever it is, mechanics solver or fluid solver, or whatever you're doing. Can you think of a part of the code that involves 28 floating point operations for every time you read or write a float? No. Most of you, there's one nodding in the back. You've got something like that? Monte Carlo? What are you doing?
Molecular dynamics.
Okay, so it's in that ballpark. You could there are some odd applications where you can do that, but most people don't have that kind of floating point load. And in fact, MD is one of the heavy users for GPUs because of this issue. Right. So,
excuse me, you said that there's an issue when you do double precision here, right?
Yeah, so you won't get 1.4 teraflops in double precision from this device. You'll get maybe a fraction of that. Well, first of all, you won't get that in single precision. You'll get some fraction of this in single precision. And then take whatever that was, and you're very likely to be memory bound unless you have a very certain application. Take that and divide it by 2. That's my guess.
I should have asked the Nvidia guy, but I was.
He's right there.
But I mean, but because you brought it up, so then, I always have, GPU and CUDA installed by somebody else.
Right.
Not by me, but what happened? I would like to buy one of them and install in my PC. Is that do I have to extra work to do it, or just plug in?
Well, if you've got someone who'll do it for you, it's no work for you, right? Yeah, so the process is you order one of these things, you plug it into the PCI slot. Hopefully you've got a PCI Express 3 slot, which will give you reasonably good bandwidth. Plug the power in. You give your computer to someone who's going to mess around with install, depending if you're running Linux or Windows. If you're going to run Windows, you can probably do it yourself. If you're going to run Linux, you might want to get someone else to do it for you. but they'll have to install drivers. They'll have to install the developer kit. And if it's in Linux, this can be quite an involved process. If it's Windows, it's pretty straightforward. But this thing is getting easier over time. Okay? Right. Okay, so certainly at the Fermi class, double precision was not a really particularly strong point, but single precision was fine. Also, other things to note is in the pre-Fermi architecture, they took out most of the cache. So you didn't have L3, you didn't have L2. L1 was approximated by shared memory. And it proved to be really difficult to program, because if you didn't schedule your data motion just right, your performance would tank. So you had a wide level of user experience. Some people got fantastic performance, and some people got really crappy performance, depending on how well they'd managed data locality. So if you're very good at managing data movement through shared memory, then you could get excellent performance. You also had to pay attention very carefully to page boundaries and making sure data access was not only page-aligned, but also what they called coalesce, so that you're looking at consecutive bytes in memory, sort of unitary stride access. If you didn't do all that stuff, performance would be worse than the CPU. If you paid attention to it, you could get excellent performance. Of course, then you started to see papers where people would say, I got 1,000 times speed up. What they're saying is that they have a really, really crappy CPU code. So you can look at every paper which says 1,000 times speed up or 100 times speed up, and you can go back and say, you don't know how to program a CPU. So what happens is, the funny thing is that when you take one of these optimized GPU codes and you backport it to a CPU, because you had to pay such careful attention to data locality, data movement, you could get speed up. Typically, people found that when they backported their GPU code to CPU, the CPU code would run faster too. And then a more realistic outcome is the ratio of the bandwidths. So if you've got 150 gigabyte bandwidth on the GPU and you've got 25 or 40 gigabytes per second on the CPU, look at the ratio and you get about a factor of 5 difference between the CPU and the GPU for a memory-bound problem. Okay? So there's some really interesting things exposed by all those papers. It can be really funny reading them. So that was the Fermi class GPU. We'll go forward one generation to the Kepler class GPU. This is not my favorite GPU architecture from Nvidia, because instead of having 32 floating point units per core, they went to 192 floating point units per core. So they 6 times as many floating point units per core. The Fermi architecture was actually, in some sense, built with HPC in mind. Nvidia Research, which is responsible for developing the HPC side of Nvidia's business, actually had a lot of input into the design of Fermi. But then the main business, the bread and butter business for Nvidia, is actually graphics processing. It's not the HPC applications. So the pendulum swung a little bit in the other direction, where we have cores which are optimized and tuned for the graphics application, not for general purpose applications. So if you look at the number of floating point units, and you look at the amount of registers, so the register file, the amount of registers available to all these floating point units did not go up substantially. The amount of shared memory did not go up substantially. So they've over-provisioned the floating point units for the graphics application, but that didn't really help out the general purpose applications, where we needed more register space, we needed more shared memory space. Okay? So this was sort of a tick-tock, where we have on the tick, you have the general purpose applications. That was the Fermi. The TOC was the Kepler, where it's more about graphics. Notice the peak theoretical flop count has gone up substantially. But you can't achieve that, because the number of registers available per thread has really gone down in a sense. The amount of shared memory has gone down in a sense. So the work you can have each thread do in a general application has been limited. Okay? Now we get to a compromise. So we went tick, tock, tick. So we have a compromise between the graphics application and the general purpose application, where if you look at a core now, the core has, in some sense, subcores. And each subcore looks like a Fermi core. So we've gone back to basically 4 Fermi cores in a typical Maxwell core. And this has a much more balanced structure so that we have more registers available, more shared memory available to each thread. Okay? So this is actually quite a sweet spot. It's a very nice card. It's a very high-performing card for graphics and for applications. So this is actually very nice. And the power requirements have gone down as they change process. Okay?
Which card is this?
This is, let's see. It's probably either a Titan or a 980. I can't remember exactly which one it is. After a while, they sort of blur it into one continuum of cards. But at least, so I say that, but at least Nvidia has identifiable generations and identifiable cards in each of those generations. I could tell you about most of the cards in a specific generation of their roadmap. Intel, I can't tell you. I mean, they have a continuum of product, but the Nvidia cards are discretely identifiable. Right. Notice that the peak performance didn't actually go up that much, but it was more attainable. You could actually get closer to peak with this card. So let's look up the ramp up in, yes, hello.
So, yeah, apologies if we might cover this later, but in the Maxwell card, is there then another hierarchy of splitting up work when you program it with CUDA?
No, but you might be able to take advantage of some newer features in CUDA. But in general, it was just easier to get good performance without actually having to tune specifically for the architecture. So if we think about this progress, this is up from the G80 where I started through the Tesla class, the Fermi, the Kepler, and the Maxwell's next. The core structure, core architecture has gone from 2 8-way SIMT units to this monster 192 floating point unit, and then we've moderated to this 4x32 unit, okay? But the funny thing is, the code I wrote for the G80 class GPU can still be used on this architecture because of the way that CUDA structures or forces you to structure your code. It's, in some sense, abstracted above the specifics of the architectures. In order to get best performance, you need to actually pay attention to the specific structure of the core. But in general, you can run your CUDA code from 7 years ago, and it still runs because it's forced you into a certain style of programming. And here's the roadmap. I'm not sure if this is still valid, but we're currently at Maxwell. I think Pascal is next. Is that what's, or has that changed? That's correct, yeah. Now, the next card is going to be a bit of a revolution, that they've changed the form factor, and I think they're also using high bandwidth memory. Is that correct? Or is that in the generation afterwards?
Yes, and I hope it's in my talk as well.
Yeah.
So the high bandwidth memory, yeah.
Right. So that fantastic high bandwidth is getting better through stack memory, collocated stack memory. So it's really, that's as a typical generic HPC guy, that's what I look for. It's not that headline floating point rate, but there are 2 things that matter to me. One is the latency, which hopefully is reduced in the new HBM, hopefully. And the other thing is bandwidth, because I just have to move a lot of data around. Now, if we talk about the sort of the hierarchy of the memory system, on device, on the chip, greater than terabytes per second data movement in terms of registers, shared memory. Between the GPU and the memory chips on the board, 330, that's going to go up to 512 or in excess of 512 gigabytes per second data movement. Then you have this bottleneck, which I believe will be improved with the next generation. And then you have another bottleneck, which is the data movement on the CPU. Okay, so you have this, in some sense, this funnel and bottleneck at the PCI Express, which I believe will be improved.